Hello, today we're continuing with our series on electromagnetic radiation, looking at the Fresnel equations. This is all part of a series where we're looking at what is light, the Poynting vector, Fresnel equations, polarization, electromagnetic waves on metals and waveguides. Among other things, the Fresnel equations will tell us how much light is reflected or refracted when light passes from one dielectric medium to another. We're talking in this video about dielectrics or insulators, such as water or glass or air. We'll deal with metals later. The distinction for our purposes today is that metals have free electrons and dielectrics don't. In the introductory video in this series, What is Light, we were introduced to two concepts, epsilon naught and mu naught, epsilon naught being the permittivity of free space and mu naught being the permeability of free space. And the operative words there are free space or vacuum. Once you have a dielectric, then you have to modify these terms by a coefficient in each case. Ke epsilon naught becomes the permittivity in the dielectric, and Km mu naught becomes the permeability in the dielectric. And Ke and Km are essentially the coefficients which modify these values in free space for their values in the dielectric, such as, for example, water or glass. And I can tell you that Km, that is the coefficient for permeability, is equal to 1 for all dielectrics. The only occasion where it is significantly different is in ferromagnetic material, and we're not going to touch that today. So as far as we are concerned today, the permeability, that is mu naught, is constant in free space, vacuum, and also in the dielectrics that we're likely to be using today. Now, we showed in the video What is Light that the speed of light in a vacuum is equal to 1 over the square root of mu naught epsilon naught. That's these values up here, the values in free space. That's why it's the speed of light in a vacuum. What that means is that the speed of light in a dielectric or media, whatever media it happens to be going through, is going to be the modified form of these two constants here. So instead of mu naught, we now have to have Km mu naught, and instead of epsilon naught, we have to have Ke epsilon naught. But 1 over mu naught epsilon naught, or rather 1 over the square root of mu naught epsilon naught, is this term here, which is the speed of light in a vacuum. So we can take this term here and we can say that the speed of light in the media is equal to the speed of light in vacuum divided by the square root of the coefficients, Km, Ke. But I've also told you that for purposes of today, Km is going to be 1. So that also goes, and we've now got that the speed of light in a dielectric media, like air, glass, water, is going to be the speed of light in vacuum divided by the square root of Ke. And if we just rearrange this equation here, we can see that the speed of light in a vacuum divided by the speed of light in a dielectric media is equal to the square root of Ke. And that we call the refractive index n. For water, and specifically for light travelling through water, the value of Ke is approximately 1.77. That's visible light travelling through water, which means that the refractive index for water is going to be the square root of 1.77, which is approximately 1.33. But it has to be said that the refractive index is highly dependent on the frequency of the electromagnetic radiation and will vary considerably. Indeed, it even varies between red light and blue light, which is of course the reasons why colours separate out when light goes through a prism. Now I just want to remind you from the video on what is light of how we described electromagnetic radiation. We took three axes. This is the z-axis, this was the x-axis, and this was the y-axis. They're all of course perpendicular to one another, and we said that the electric part of the electromagnetic wave was a, as it were, sine wave where the electric field oscillates in the x direction, but that the wave as a whole travels, of course, with the speed of light c, which is equal to 1 over the square root of epsilon naught mu naught in a vacuum, and it travels at the speed of light c in the z direction. So the E field is oscillating up and down in the x direction, the whole wave is moving in the z direction, and that there is an associated in phase B field which oscillates, can't draw it terribly well, oscillates in the y direction. So the B field is oscillating at right angles to, or perpendicular to, the E field, which is oscillating in the x direction, and both of them are perpendicular to the direction of travel, which is in the z direction. And we said that if you want to know which way the B field oscillates in respect of the E field, you use the E cross B, or the corkscrew rule. That is to say, you take the E field, which is in the x direction, and you turn it towards the B field in the y direction, and you ask yourself, if that were a corkscrew, which way would the corkscrew move? And of course, if the corkscrew is being twisted from x to y, it will move in that direction. So E cross B, or twisting the x to the y coordinates, tells you which way the corkscrew will move, and hence which way the wave will move. So essentially, if you were to look head on at this wave, in other words, that wave is coming out of the paper towards you, what you would see is an oscillating E field in the x direction and an oscillating B field in the y direction. And remember that we showed that the B field is c times smaller, the speed of light times smaller than the E field. So you would see a large oscillating E field and a very small oscillating associated B field. But here's the next key point. Light, or the electric field of light, does not have to oscillate only in the x direction. It can oscillate in any direction in the xy plane. That is to say, if you're looking head on, it doesn't only have to oscillate in the x direction. It could, if it wanted to, oscillate in the y direction or in any direction it chose. That is called unpolarized light. The E field oscillates in any direction. Any direction in the xy plane. It cannot oscillate in the z direction because it must oscillate perpendicular to the direction of travel. If the direction of travel is the z direction, then the only way it can oscillate is somewhere in that xy plane. And of course the waves will oscillate in all directions. There will of course be an associated magnetic field for each of these directions of oscillation, and that B field will always be perpendicular to the E field in the xy plane. Again, the B field cannot oscillate in the z plane or in the z direction because that's the direction of travel, and it must always be perpendicular to that. Now, whichever way the E field oscillates in the xy plane, let us just for the moment assume that that is the E field oscillating at some angle in the xy plane. We can always resolve that into its constituent parts. We can have an EX component and we can have an EY component. remember we're looking head on at the wave coming towards us, so the X field actually is coming out, the Z coordinate is coming out of the paper. So we've got X and Y and Z coming out of the paper. And I just remind you again, the E field cannot have a Z coordinate if Z is the direction of travel of the wave, because E must always be perpendicular to the direction of travel of the wave. So now we're going to consider an electromagnetic wave that travels from one dielectric medium to another. For example, it could go from water to glass. Each of these media is going to have values of the coefficient for permeability, the coefficient for permittivity, and the refractive index. And those are going to be, I'll give them the number 1 to distinguish them for medium 1. And then there are going to be values for the permeability, the permittivity, and the refractive index in medium 2. As it happens, I've already told you that Km1 will equal Km2, and that will be 1. But we'll keep them there just for the time being. And we're going to consider the electric field vector in medium 1 and medium 2. This is not the direction of travel of the wave, this is the electric field vector. And let's say it's like that in medium 1 and it's like that in medium 2. And once again we can always resolve those fields or those vectors into the constituent parts, which I'm going to call vertical. So this is the electric field vertical in medium 1, and this is the electric field horizontal in medium 1, and this is the electric field vertical in medium 2, and this is the electric field horizontal in medium 2. Now you might argue, and this is of course the actual E vector in medium 1 and medium 2, and you might argue that the two should be the same. Why would they change? Well, that is what we need to establish, and the way we're going to do that is we're going to look at what is called the boundary conditions. In other words, what happens when the electromagnetic radiation goes from this medium to this medium? What happens at the surface or the boundary? And we get those boundary conditions from good old Maxwell's equations, and here they are. Those are the 4 Maxwell equations which we derived in the video on Maxwell's equations. They are called the integral form of Maxwell's equations because they start with integrals. And you'll notice that there are 2 which have dot dA terms and 2 which have dot dL terms. And I'm just going to give you a handy hint or a trick for how we're going to deal with these. Where you have a dA term, you use a pillbox. Where you have a dL term, you use a rectangular loop. And if that doesn't mean anything at the moment, keep watching and you'll see what I mean. We have 4 Maxwell's equations, so they will give us 4 boundary conditions. And we'll start with the first. And if you can remember that, it was that the integral of E dot dA is equal to sigma q, the sum of all the free charge, divided by epsilon 0. Now, because we are in dielectrics, we're going to have to modify this term epsilon 0 to be Ke epsilon 0. So in other words, we need the coefficient as well as the actual value of epsilon 0. And that means we can multiply through, so we get that Ke epsilon 0, Ke epsilon 0 times the integral of E dot dA is equal to the sum of all the charges enclosed. And here's the first important point about dielectrics. As we've said, dielectrics don't have any free charges. Metals do, but dielectrics don't. So consequently, the sum of all free charges in a dielectric will be 0. So now let me redraw this diagram here and show you how we use the pillbox, because it's a dot dA term, to solve the problem. So here is the electric field vector with its constituent parts EV1 and EH1 in medium 1, and here is the E vector with its constituent parts EV2, EH2 in medium 2. And what I'm going to do is to construct what's called a pillbox, or if you like, a cylinder. And the area at the top of the cylinder I'm simply going to call A, and the height of the cylinder I'll call L. This is the surface between the two dielectrics, 1 and 2, and what we're considering is an electromagnetic wave that is travelling from medium 1 into medium 2. And we're considering how the electric vector, and more specifically how the components of the electric vector, change as the electric field moves from one medium to the other. So what we've got to do is simply take our equation here, and we're considering the dot product of the electric field through the area. Remember that a dot product is 0 if the two vectors are at right angles. So let's consider which of these E fields is going to go through what area. Well, obviously the vertical components of the E field will go through the top or the bottom. In this case, EV1 will go outwards through the top, EV2 goes inwards from the bottom. There will be no components of, or there will be no value of EH1 and EH2 going through the top or the bottom because they're going parallel to it, so they can't go through. Similarly, EH1 and EH2 will go out through the sides. No value of EV1 or EV2 will go out through the sides because they're obviously going parallel to it. So what we can do is we can take this equation here and we can say that as far as EV1 is concerned, we're going to get that KE1, because it's in medium number 1, times epsilon naught times EV1 through the area A. EV1 goes through area A. Now we'll have minus KE2, because we're now in medium 2, epsilon 0 EV2, that should be EV1 by the way, times A. It's minus because in this case the EV1 vector is going out through the area. In this case EV2 is coming in through the area. And now we're going to have to add some set of terms which represent the value of the E fields, the horizontal E fields, which are going out through the side. And for these purposes I'm simply going to call that gamma. There will be some terms going out through the side. As we shall see in a moment, that won't matter. And that all equals 0, because that's what we had up here. So essentially we've taken the integral term and we've simply made it a sum of the vertical E fields, or components of the E fields, which go out through the top and bottom of the pillbox or cylinder, and the EH fields which go out through the sides. Now comes the clever bit. We reduce L to 0 at the surface. So we just, in other words, we shrink the pillbox or the cylinder until it is simply a two-dimensional pillbox sitting on the surface. So when L goes to 0, how much of the EH term can go out through the sides? Well, there are no sides because we've shrunk the sides to 0. Consequently, that term disappears. And because we've got an equation which equals 0, we can divide both sides, if you like, by A. So A now disappears. We can also divide both sides by epsilon naught. So epsilon naught disappears. And we can take the remaining term here on the other side of the equation, and that will give us that KE1 times EV1 equals KE2 times EV2. And that is the first boundary condition. So what we've actually found is that the respective size of the vertical components of the E field change as the electric vector moves from one dielectric to the other, and the extent to which they change is determined by the coefficients of the permittivity factors. Now I want to stick with E fields for the moment, so we're going to look at the third Maxwell equation, which is the E dot dl term. So that's the integral of E dot dl is equal to minus d phi b, that is the magnetic flux, dt. And now I'm going to draw my same diagram again. Here's my surface between media 1 and 2. Here is my E field in media 1 with its component parts EV1, EH1. Here it is in medium 2 with EV2 and EH2, the constituent parts of the electric field in the two media. And this time I said that the secret was not the pillbox, but this is a DL term, and for that you use a rectangular loop. So here is my rectangular loop, which I can construct. I am entirely entitled to construct any loop I know I like, and I'm going to walk around that loop in this direction. And what Maxwell's third equation basically says is that the integral of the E field with the distance as I travel around that loop is going to be equal to, give or take a change of sign, the rate of change of flux through the surface that is constructed by my loop. It's a dot product, E dot dl, so there will be no dot product if two vectors are at right angles to one another. So let us first just think about my journey from here to here. The only E vector that's going to apply is EV1 because EH1 is perpendicular, so there will be no dot product. So there will be an EV1 term that will come out of this journey here. But whatever that is, it will be exactly balanced by the return journey here. So that part of the journey and that part of the journey will cancel out. Similarly, that part of the journey, whatever the EV2 contribution to that part of the journey, there will be no EH2 contribution. Whatever the EV2 contribution here is, it will exactly match the EV2 contribution in that part of the journey. So the only two bits of the journey that are going to constructively add to this are going to be my journey from here to here and my journey from here to here. So what's that going to be? Well, here to here we've got EH1 times, so let's say that this distance is, we'll call this L again, I think. So now we can say that here we've got EH1 times L, EH1 times L as we go in that direction. When we go in this direction, we're going in the opposite direction, so that will be minus EH2 now times L. These are the E dot dl terms. The integral simply now becomes a sum. And those are the only two terms that actually are going to have any effect. And that's going to be equal to minus d phi b by dt. Now we're going to do exactly the same thing as we did before. We're going to shrink the path so that it becomes infinitesimally small at the surface. If we do that, what is the area associated with that path? Answer, 0. There is no area because we have shrunk this down to just essentially a straight line, or at least a rectangle that is infinitesimally small. So what is the flux that can go through an area that is infinitesimally small? It is 0. No flux can go through. And so now we can cancel the L terms and we get the second boundary condition, which is that EH1 equals EH2. That's the second boundary condition. And that tells us that as the E vector goes across from medium 1 to medium 2, its horizontal component does not change. What we say is that the tangential, if you like, or the horizontal component of the electric field is continuous. That was not true, remember, for the vertical component. Now we need to do the same thing for the other two equations which deal with the magnetic field. We've got a B dot dA and a B dot dL equation. And just as we did with the electric fields, we can take our surface between our two dielectrics, 1 and 2, and now instead of considering the E field, we can consider the associated B field. So let's say that those are the B fields of the wave that is moving from medium 1 to medium 2, and they can be split into their coordinate parts, BV1, the vertical component, and the horizontal component in medium 1, and the vertical component BV2 and the horizontal component BH2 in medium 2. And the Maxwell equation that we're using is the second. The integral of B dot dA is 0. The integral of B dot dA is 0. So it's a B dot dA term. For that you use a pillbox. So I'm going to draw my pillbox around the B fields. And in exactly the same way as we said before, we're going to get a BV1 term going through the top of the pillbox, which has cross-sectional area A. We're going to make the height of the pillbox or the cylinder L. We're going to have a BV1 term going out through the top area. We're going to have a BV2 term coming in from the bottom. And we're going to have the BH, the horizontal terms, going out through the sides. The horizontal bits don't go out through the top, and the vertical bits don't go out through the side. So our integral becomes essentially a summation term of BV1, in other words our vertical vector here going out through the area at the top, minus, because this is now coming in the opposite direction, it's coming in rather than going out, so minus BV2 times the area at the bottom, plus the famous gamma term, which is everything that's going out at the sides. And that we know equals 0 because that's what Maxwell's equation tells us. Well, now we're going to do exactly the same trick as before. We take this cylinder and we reduce it to essentially a two-dimensional cylinder on the surface. So L becomes 0. When L becomes 0, no B fields can go out through the side. So that is cancelled. The A's cancel, and now you get that BV1 equals BV2. So the vertical components of the B fields transport across the boundary. Remember, the vertical components of the E fields did not. And that is essentially the third boundary condition. That just leaves us with one more to look at, and that is this B dot dL term here. Let's write that down. That is the integral of B dot dL is equal to mu 0 I plus mu 0 epsilon 0 d phi E by dt. Now let's just look at that for a moment. We can write that as, take the mu naught out on both sides, and that gives you 1 over mu naught into the integral of B dot dL is equal to I plus epsilon naught d phi E by dt. What is I? That is the current. What is a current? It is the flow of electrons. Are there any electrons flowing? No, because we're talking about a dielectric or an insulator that has no free electrons. So there can't be a current. So that disappears. And now, because it's a dot dl term, we use the rectangular walk. So we redraw our diagram. Here's our surface. Here are the constituent parts of our B field, V1, BH1. Here in the medium, that's in medium 1, here is in medium 2, BV2 and BH2. And we construct a rectangular path around. And remember that what we're saying is that the integral of B dot dl as we go through around the path is now going to be equal to epsilon 0 times the rate of change of electric field through the area created by the path. So what is that going to be? Well, we're going to have, in exactly the same way as we had before, the contribution of BV1 as we go from here to here will be exactly compensated by the contribution of BV1 when we travel in the opposite direction. There will be no BH1 in those directions because we are going perpendicular and it's a dot dl term. If the two vectors are at right angles, there's zero effect. And for the same reason, the contribution of BV2 when we go that way will be exactly matched by the contribution of BV2 when we go that way. So once again, the only contributions we're going to get are when we move in that direction along the top and when we move in that direction along the bottom. And we're going to say that the length here is going to be the length L. And so we're going to get BH1 times L is going to be the contribution along the top. The contribution along the bottom is going to be minus because we're going in the other direction. BH2 times L. And that's, we've got to remember that these are each divided by their respective coefficients of the permeability. So in this case we have to divide by Km mu 0, sorry, Km1 mu 0 because it's the permeability in medium 1. Here we have to divide by Km2 mu 0 because it's the permeability in medium 2. And that is going to equal, from up here, epsilon 0 times d phi E by dt. Epsilon 0 times d phi E by dt. Okay, guess what we're going to do? Exactly the same as we did before. We just shrink this rectangular path down to an infinitesimally small area on the surface. An infinitesimally small area. How much flux can travel through it? 0. This just becomes 0. I also told you that Km1 equals Km2. So essentially these two terms are the same. So they cancel, and L's can cancel, and that gives us our fourth boundary condition that BH1 equals BH2. The horizontal components of the B field, transport across the boundary. In other words, the horizontal component of the B field is continuous, and that is the fourth boundary condition. So now we have all four boundary conditions that we're going to need to help us construct the Fresnel equations. But by way of a bit of a break, I thought you might like to see the dogs that I have that frequently bark and interrupt my videos. Now have to have Km mu naught, and instead of epsilon naught we have to have Ke epsilon naught. But 1 over mu naught epsilon naught, or rather 1 over the square root of mu naught epsilon naught, is this term here, which is the speed of light in a vacuum. So we can take this term here and we can say that the speed of light in the media is equal to the speed of light in vacuum divided by the square root of the coefficients, Km, Ke. But I've also told you that for purposes of today, Km is going to be 1. So that also goes, and we've now got that the speed of light in a dielectric media, like air, glass, water, is going to be the speed of light in vacuum divided by the square root of Ke. And if we just rearrange... Hello, today we're continuing with our series on electromagnetic radiation, looking at the Fresnel equations. This is all part of a series where we're looking at what is light, the Poynting vector, Fresnel equations, polarization, electromagnetic waves on metals, and waveguides. Among other things, the Fresnel equations will tell us how much light is reflected or refracted when light passes from one dielectric medium to another. We're talking in this video about dielectrics or insulators, such as water or glass or air. We'll deal with metals later. The distinction for our purposes today is that metals have free electrons and dielectrics don't. In the introductory video in this series, What is Light, we were introduced to two concepts, epsilon naught and mu naught, epsilon naught being the permittivity of free space and mu naught being the permeability of free space. And the operative words there are free space or vacuum. Once you have a dielectric, then you have to modify these terms by a coefficient in each case. Ke epsilon naught becomes the permittivity in the dielectric, and Km mu naught becomes the permeability in the dielectric. And Ke and Km are essentially the coefficients which modify these values in free space for their values in the dielectric, such as, for example, water or glass. And I can tell you that Km, that is the coefficient for permeability, is equal to 1 for all dielectrics. The only occasion where it is significantly different is in ferromagnetic material, and we're not going to touch that today. So as far as we are concerned today, the permeability, that is mu naught, is constant in free space, vacuum, and also in the dielectrics that we're likely to be using today. Now, we showed in the video What is Light that the speed of light in a vacuum is equal to 1 over the square root of mu naught epsilon naught. That's these values up here, the values in free space. That's why it's the speed of light in a vacuum. What that means is that the speed of light in a dielectric or media, whatever media it happens to be going through, is going to be the modified form of these two constants here. So instead of mu naught, we change this equation here. We can see that the speed of light in a vacuum divided by the speed of light in a dielectric media is equal to the square root of Ke. And that we call the refractive index N. For water, and specifically for light travelling through water, the value of Ke is approximately 1.77. That's visible light travelling through water, which means that the refractive index for water is going to be the square root of 1.77, which is approximately 1.33. But it has to be said that the refractive index is highly dependent on the frequency of the electromagnetic radiation and will vary considerably. Indeed, it even varies between red